How does the detection of the gravitational waves increase our vision, or how we see the universe? Does it increase the distance, or just does it improve our understanding of the makeup? How does the
Okay, you really want to know about gravitational waves instead of just...
Well, part of our story is that
okay.
radar is increasing vision. First it was over the horizon.
Fine. I'll gladly give you an analogy. Okay, let me try something. And for some reason, I'm in trouble this morning. I don't know why.
Probably doing more talking than usual.
No, the joy of gravitational waves is that it allows you a completely different view of the universe, a view that we've never had before. And let me try to give you some examples of that. All the things we know about the universe up to now come from what we call electromagnetic radiation. In other words, radio waves, or infrared waves, optical waves, things you can see, X-rays, gamma rays. All of these different channels that we have for looking into the universe tell you what's going on in different stellar systems and galaxies and stuff like that. But all of them depend on the same phenomena. You're moving charges to make electromagnetic waves. It turns out that gravitational waves come from the process of jiggling masses. Jiggling mass, we accelerate mass, and it makes a gravitational wave. So it doesn't involve charges at all. And so you get a different view of everything. And part of it is that because of this, and let me say, it's been very, very difficult to detect gravitational waves. I mean, that's been a struggle for close to 40 years to try to finally do it. Now that it's been done, you can capitalize on that. And this is sort of a funny way of looking at it. You can capitalize on it because the same problem, the problems you have with electromagnetic radiation is that electromagnetism interacts, the radio waves and all the electromagnetic waves interact with all the other charges around. So when you now look, for example, at a star, you only see the surface of the star with electromagnetic waves. You may only see the outer part of a system. And because if you try to look deeper into the system, it's all been scattered. The radiation that's comes to you can't come from the inside of the star. It gets scattered out, and all you see really is the surface of the star. And it's different for different wavelengths. For example, with electromagnetic radiation, you can look a little deeper into the star because it doesn't scatter so badly. But optical radiation, you only get probably a little depth into a star or into a system which is full of plasma. The interesting thing about gravitational waves is since they are generated by masses and they only interact with mass, you can look all the way inside a system. It's the same reason we've had a hell of a time detecting them. They don't like to interact with things. But once you have an instrument that lets you see them, it allows you to look deep inside everything in the universe. You can look at things you never saw before. For example, suppose we're lucky enough to have a supernova, which is the explosion of a star. With electromagnetic radiation, you can only see the outer parts of the explosion. But with gravitational wave astronomy, you can look right in and see what the motions are of the inner pieces of the explosion. You can see the oscillations of the masses. You can see everything. And so consequently, all that information comes pouring out of the system. It's not in any way affected by its travel to us because it's so inert. It doesn't interact with anything. And we can maybe ultimately in the very, very distant future, that's not going to happen with the instrument we have now, actually look at the moment when the universe first got created. Because we can look through the plasma. That makes it so that we can't now look any closer to the beginning of the universe than 300,000 years after the big explosion. We can't, with any light or anything like that, look deeper into that because this plasma scatters everything. But gravitational waves we can go right to the beginning. Now, let me not give you too much of a pep talk on that. It's not easy to do, and I hope other techniques besides LIGO or the direct detector will detect it first. There are some ideas, and people think they might be able to detect it indirectly, the gravitational radiation from the very beginning. But it's because of the gravitational waves that you can do this. And we will try, I mean, with these instruments. Once we need better instruments than we have now to try to do that.
So these black holes colliding had to be an incredibly, lack of a better term, loud event, right?
Well, the
So-
black holes colliding was probably the strongest event that ever was. I mean, in fact, when you look at the amount of energy that went into gravitational waves, and I'll give you the number. Here are these things which are sort of 30 solar mass objects. They form a new black hole. It turns out the new black hole that isn't equal in mass to the sum of the two masses. 3 solar masses, about 5% of the energy of that system has been lost into gravitational waves. Okay? Solar masses, mind you, that's the amount. And now when you say what is the intensity or the amount of power that has been radiated by that, you find out it's something like 10 to the 5, well, it's about 10 to the 4 times more, 10,000 more energy in that thing than what the whole universe, and not energy, but power. That's energy per time, okay? It didn't last very long. But during that little instant when the thing was sending out its gravitational waves, there was more power in those than there was in the whole universe at that moment. It's in the power in terms of the emission of light, emission of particles and everything, just for that brief, it's 10 milliseconds, 20 milliseconds.
And
Yeah.
is the equipment detectors you have now, so could it detect, like you're discussing a supernova? Could it?
Yes, it could. But the joy of this is that we saw not only one of these, the one that made the news, and the one that we are sure of is a great big one. I mean, by the way, so you get an idea, that the one we saw is 1.3 billion years away. That took light 1.3 billion years to get here from that. So it's not at the outer edges of the universe, but it's pretty far out. And so it's very much diluted by the time it gets here. But we know from our data, which we haven't all analyzed, that we were lucky very in the beginning of the run, we saw this enormous one. But we are quite certain that there are others in the data which we have still yet to analyze. And there may be as many as 2 or 3.
Were you looking? Were you?
Oh, no, you always know, there's no focusing.
Okay.
These things, the joy of these, and also the nastiness, both and joy and unhappiness of these detectors, is they don't have much directionality. They're not like telescopes. They become telescopes when you use them in pairs or triplets or in groups, because then timing information, when a pulse gets to one detector and the delay time, and if you have multiple detectors, you can then sort of, by triangulation, determine where the source is. And that's something that will improve as we get more antennas on the air.
I know you don't have much time, maybe 3
Yeah.
more questions.
Yeah.
Is this the first time we saw the event horizon? Wasn't the event horizon something that we've been struggling to see or detect?
That's a good question. Let me think about that for a moment. Is this the first time? Well, we have other black holes in the system. The black holes we know, the one we know the best, is the one that's lurking right in the middle of our own galaxy. And that weighs 100,000 suns. Now, there's an experiment going on right now to try to see things that approach the event horizon of that big black hole. It's a very big interferometer experiment using radio waves. Again, derivative of RadLab. Okay? But I think I can say with pretty good assurance that there is no other observation that has ever been made where we saw anything that has to do with the event horizon in a black hole. This is the first time. We will see event horizons of other holes as from this experiment of the observation of our own black hole. But we will see it more and more because I'll tell you, we will see more once we get back on the air and we make even slight improvements in the apparatus. We will see we might be seeing an event per month right now. I can't prove that, but it's close to that. As soon as we improve the apparatus by, let's say, a factor of 2, which we should be able to, meaning improve its sensitivity by 2. And we're not at design sensitivity yet. We would then get not one event per month, but we multiply 10. That's close enough. It's the cube of 2 is what we get in improvement. And so you get events every 3 days. And if you improve it every time you improve a little more, you increase the event rate. So soon, I don't know when soon is, it could be a year, 2 years from now, we will be looking at a lot of different black holes, and they become very much more like astronomy. People will start making catalogs of black holes that do this kind of singing and that black holes that do the other kind of singing. Some will have spin, some will not have spin. I mean, it'll be quite a, it'll become like botany again,
So you can detect waves without a collision or without...
Well, that's a good question. They're different. There are more sources than black holes, is what you're really asking. What we see is only when we see them only when they do something. No, it's sitting there, they don't radiate gravitational waves. That's, every time they eat something, they will radiate gravitational waves. And that's one thing we will be looking for. So will other projects be looking for that.
So we've been able to see it right up until it gets to the point of entry and then we lose it?
Well, you see, that's a good question. You ask, how does the event horizon get into, let's say, what is the event horizon? The event horizon is exactly what you were alluding to, namely it's that place, at least for us on the outside of the black hole, which separates the inside of the hole and the outside of the hole. And people will never approach, we can't, it is, as you get closer and closer, you put things, clocks, and you put them at different distances away from the center of the black hole and approach the event horizon. You will see them getting slower and slower and slower and slower, and so slow that you can never see something from a distance fall in. But if you're at the black hole, you don't have that. In fact, if you're at the black hole, it looks quite terrible. You cross the event horizon, and there are many books written about this. And what happens is you begin to feel a terrible pull on you. It's the pull of the whole black hole. You're getting sucked in, but it's not just that pull. It turns out because there's gradients of that pull. In other words, your feet are, let's suppose you're walking, you're falling in straight. But like this, you're going right in. Your feet get tugged much more than your head does. So you get stretched. And as you fall in, you get stretched more and more and more. And eventually you get torn apart.
Right.
And then that's not the end of it. Then the things that have been torn apart get torn apart. The atoms get torn apart. The nuclei get torn apart. Everything gets torn apart.
So is a black hole just a destruction machine? Or
well, it's the end result of a stellar collapse. I mean, it's a star. That's one way we make them. One way they can be made. But one way to think about the place is and I suspect there'll be many papers now written about different ways of making black holes. That in nature that may happen. But what happens in the end is the black hole loses all information about what it came from. That's a big discussion, but it turns out only three things remain after the black hole has disrupted the thing that fell into it. It's the mass of the hole, that's one of the properties, that's how much curvature of space-time you get from the hole. The other thing is